Now let's learn about Dijkstra's algorithm, which is a shortest path algorithm. First of all, why do we need this shortest path algorithm? Because we talked about another shortest path algorithm, which is called BFS, breadth first search. But the downside of that is it only works when the edges in our graph are not weighted. So when we're given unweighted graphs, it's equivalent to being given a graph where every edge just has a weight of 1. In that case, how can we find the shortest path given some source node? For example, let's say A is our source node and we have a bunch of nodes in the graph and we want to find the shortest path from A maybe to D. How would we do that? Well, we would go breadth first search. We would go layer by layer. What are all the nodes we can reach with one, jump, with one edge? Starting from A, this is the first layer of nodes. And then we would do BFS on those nodes. So asking ourselves, which nodes can we reach within 2 edges? Well, in this case, we can reach the remaining nodes within another jump. So within 1 node, we can reach all these. Within 2 nodes, we can reach these. By doing this, not only did we find the shortest path from A to D, but we essentially found the length of the shortest path from A to every node in the graph. Essentially, we found that the length from A to these 2 is simply 1. The length from A to these 2 is simply 2. But what if I change the weight of this edge from being 1 to being 10? Then what? Let's try the BFS way. What are all the nodes we can reach within 2 edges? These 2 nodes, of course. But the cost of reaching C is going to be 1. The cost of reaching B is going to be 10. Even though it was just 1 edge, the cost was so much higher. And then within 2 jumps, we can reach, these 2 nodes as well. But not only that, but actually we can take an alternative path that takes 2 edges starting from A to get to B. So it took 2 edges, but the total cost of that was only 2, as opposed to this path, which took 1 edge, but the cost was 10. So BFS is not sufficient for finding shortest paths when we're given edges that have weights. Dijkstra's algorithm, though, can solve this problem for us, and actually it's very, very similar to BFS. So to set up the problem, we're given a graph with some nodes and edges starting from some arbitrary node. In this case, it's A. We want to find the length of the shortest path. Looks like there's a typo here, but ignore that. The shortest path to every other node in the graph. So our output is going to look something like this. Well, in this case, we're including A in the output. Well, what's going to be the shortest path from A to A? Well, there's not necessarily a self loop here, but the value that we put here actually is going to be important because we're going to use it to implement our solution, but we know the length is going to be 0 essentially. So the idea behind this algorithm is that we're of course going to start at A, and we are going to do a breadth first search actually, but it's a greedy breadth first search, meaning we have from A 2 edges going out. We have an edge going to node B, it has a weight of 10. We have another edge going to C, which has a weight of 3. Among these 2 neighbors, which one do you think we should visit first? Probably C. But what do we know about C? Do we know for sure that this is the shortest path from A to C? Of course we do. Can you figure out why by looking at this picture? We already know that C, the shortest path from A to C, is 3. The reason is that there's only 2 possible paths we could take from A that leave A. We could go to B and we could go to C. If we go to B, we incur a cost of 10. Now, there might be another path from B that takes us to C. In this case, there's not, but there could have been. Is it possible that that path from B that takes us to C is going to be shorter than 3? It's impossible. And the reason is that we're assuming that we don't have any negative weights in our graph. None of the edges are going to have a negative weight. That's the assumption that we're making. So if that's the case, since we already incur a cost of 10, we're never going to recover from that. When we took the other path, we only had a cost of 3. We can't beat that going the other way. It's just not possible. And even more than that, actually, when we do this breadth first search, we're going to now visit C because it was the shortest path. But now, how are we going to continue this breadth first search? Don't we have to go through all of the neighbors of A? Not necessarily. We don't necessarily have to visit B just yet. Now, actually, we have multiple choices. These are the 2 nodes that we visited so far. And actually, at this point, A would be marked with a cost of 0. But these are the 2 nodes we visited so far. Now we have several choices. We can take this edge that costs 10 that takes us to B, or we can take this edge that takes us to E, which costs 2. Actually, though, we wouldn't only care about the 2. We would take 3 plus 2 into account because we want to know what's the cost from A to E. We don't care about from C to E, so we want the total cost. So here we would say the cost to reach E is going to be 5. The cost to reach B is going to be 10. But hold on, there's a couple more. From C to reach D, the cost is going to be 8 plus 3. That's 11. That's another choice we have. And the last choice we have, actually, we can reach B a second way with an edge of 4 plus 3, so that's 7. So actually, in this case, there's a shorter path from B. We don't even have to take this way. We can go directly like that. So that's the idea behind this algorithm. Among all of the choices we can make, in this case, we have 1, 2, 3, 4 choices. We always want to pick the choice that's going to take the minimum cost, that's going to be the shortest path. And in this case, among these 4 choices that we have, the shortest path is going to be this one because the total cost of that is going to be 5. So if we know that the total cost of reaching E is 5, and that's smaller than all the other choices that we currently have, then none of those possible choices are ever going to lead us to a path that takes us to E that's ever going to cost less than 5. Because going to D itself is costing more than 5. Going to B here is costing 7. Going to B this way is costing 10. None of those paths are ever going to lead us to a shorter path than this one that we have right here. So the idea behind Dijkstra's algorithm is that we have a frontier. Our frontier is the nodes that we've visited so far, the nodes that we've calculated the shortest path for so far. And among that frontier, we want to consider all the outgoing edges. And among those edges, we want to choose the one with the shortest path. Not just the shortest path of that individual edge, but the total cost, the total path from the starting to that target node. So among those, we want to take the minimum. So we're actually going to need another data structure for this. A data structure that we've covered, which is called a min heap. This is one of the use cases of that data structure. So now to finally set up the problem, we're going to have a min heap where we add a pair of values. At least that's the way I like to do it. The key of the min heap is going to be the cost. That's the first value in our pair, and the second value is going to be the node, because we want to pop the nodes reachable from our frontier that have the lowest cost. We want to do this in a greedy way. And by the way, this output is going to be a hash map. At least that's the easiest way to do it, because for each node, we want to map it to the minimum cost to reach that node. The way we're going to initialize this is pretty much empty, but the way we're going to initialize our heap actually is by taking the starting point, which is A, and we're going to add it with a cost of 0, and the node is A. And then the algorithm is pretty straightforward. We're going to continue while our min heap is not empty. We're going to pop from it. So the first node that we pop, no surprise, is going to be A. We're going to find that the cost to reach A is 0. We're going to look in our hash map. We're going to see that we haven't calculated the length of the shortest path for A yet, but now we have it. It's 0. So this is the first node in our frontier. It's the first node we've visited so far. And now we're just going to go through its list of neighbors. Since we're going through that list of neighbors, you can probably tell that the easiest way to represent this graph is going to be with an adjacency list. So we're going to go through the list of neighbors of A and push them onto the heap. But what we're going to push is going to be the cost to reach each of these nodes. We have two nodes in this case, B and C. What we're going to push on is going to be the cost to reach B, which is going to be the cost to reach A, which was 0, no surprise there, plus the cost of that single edge. So 0 plus 10 is going to be 10. That's the cost to reach B. And do the same thing for C. The cost to reach C is going to be 0 plus 3, so push that onto our min heap. So now rinse and repeat. We're going to pop from our min heap the one with the smallest cost. It's C. We pop C. The cost to reach C was 3. So now we have that information. Now for C though, we're going to go through its frontier. We're going to go through all of its neighbors. We have a few of them. We have E. So when we push E onto the heap, we want the cost to reach E. It's going to be the cost to reach C, which was 3, plus the cost of that edge, which is 2. So 3 plus 2 is going to be 5. So we're going to add a cost of 5 is to reach E. We're going to push that onto the heap. Then for D, we're going to get 8 plus 3, that's 11 to reach D. And hold on now, we can also reach B. We definitely want to push that information, especially in this case, because this is going to be the shortest path to reach B. So we have 4 plus 3 is the cost to reach B from C. So we add that. 7 is the cost to reach B. Notice how B is pushed to the heap multiple times. That's perfectly fine because as long as we put the shortest path to reach B in our result, we're perfectly fine with adding it to the heap multiple times because we know among these two, which one are we going to pop first? The one with the smaller cost. So after we pop this one, we're going to put 7 as the cost to reach B. And then when we pop the second one, we're going to see that we already have the result for B, so there's no need to, put a larger value over here. But for now, let's continue with our solution. We're going to pop the one with the smallest cost, which is E. So to reach E, we get a cost of 5. Now let's get all the neighbors of E. Well, it doesn't have any neighbors, so we don't have to do anything in this case. Our heap stays the same. So let's pop again from our heap. This time we're going to pop B because it has a cost of 7. So we got the cost to reach B. It's 7. So this is part of our visited nodes. We just have a single node left. But let's get the neighbors of B. It just has a single neighbor, which is D. What's the cost to reach D? It's not just 2, remember. It's going to be the cost to reach B, which was 7 plus 2. So we're going to add 9 is one of the ways we can reach D. Good thing we did that because now we found a shorter path to reach D. The other one we had costed 11. That's why this greedy algorithm works, because we always take the shortest possible path at every single step. That guarantees that for our result, we'll also find the shortest possible path for every single node. So now finally among these, let's pop the one with the smallest cost, which is D. So 9 is the cost to reach D. At this point, our result is complete. But depending on how you code this, the algorithm might still run. We might still add the neighbors of D, which in this case is going to be E. So we would probably add like a 14 with E. And depending on how you code this, we might still end up popping every value from the min heap, even though our result is essentially complete. Or you could stop after the result is complete if there's a way that you can calculate that. But that's the idea behind this algorithm. Now let's analyze the time complexity before we jump into the code. So to analyze the time complexity, first recall if we have a graph, let's say with V vertices, by vertice I mean node, what's the maximum number of edges we could have? Well, it's going to be equal to V squared because every single node could be connected to every other node. So that's simple so far. The other thing is when we push and pop from our min heap, The size of our heap in the worst case could be the number of edges in the graph, because as we saw, we might add the same node, B, for example, multiple times to the min heap, one for every edge that's going into that node. So the size of our heap in the worst case will be E, which is going to be, in the worst case, V squared. So pushing and popping from the heap is going to be a log E operation in the worst case. How many times in the worst case are we going to push and pop from the heap? Well, we might have to do it for every single edge in the graph, because if that's going to be the size of our heap, we might, in the worst case, pop as many times as we have to. We might keep popping until the heap becomes empty. So in that case, we would do E operations, that's the number of edges, multiplied by log E, which would be the size of our heap in the worst case. So that is actually the time complexity of Dijkstra's algorithm, though sometimes you see this written in a different way. Sometimes you'll see people write this as E times log V. Why is that the case? As I mentioned, the number of edges is actually going to be, in the worst case, V squared. And the way logarithms work, this can actually be reduced to 2 times log V. We basically take that square and then move it here. That's just a property of logarithms. So this can be actually reduced. We get rid of the constants, can be reduced to E log V. So that's why, people will reduce it to this, because even though it's E log E, it can be, mathematically reduced to E log V. And this is, I guess, a more tight boundary. And, sometimes you might even see it be written as V squared times log V, but I think that's a bit less precise, because we might not necessarily have V squared edges in the graph. So I think probably the most correct way is E log V. That's, I think, the most common way you'll see this written, the time complexity for Dijkstra's algorithm. Now let's take a look at the code. Surprisingly, it's not quite as bad as you would think. It's pretty similar to BFS. So this is what the shortest path code would look like. This is assuming that we're given a list of edges. So for example, an edge from B to D. The edge will have three values, where the first value is the starting node, for example, B. The second value will be the ending node, the destination node, D, for example, in this case. And the third value will be the weight of that edge. In this case, it's 2. So it will be a 2-dimensional array, where the nested array is an array of 3 values that I just talked about right now. So like I said, the easiest way to traverse this would be with an adjacency list. So when we're given just a list of edges, what we want to do is convert it into an adjacency list. Let's say we're also given the number of nodes. So in this case, we're given 5 nodes. That would be a parameter n. So what I would do, in this case, the nodes are characters. But let's say for this code, the nodes were integers. So if we're given an integer 5, let's say we know that each node is going to be labeled, with integers between 1 through 5. So there's going to be a node for 1, 2, 3, 4, and 5. So what we would do is essentially, for our adjacency list, which is a hash map, we would go through each integer from 1 through 5 and give that node a list of neighbors, which is going to be an empty array of neighbors initially. And then we're going to go through the actual edges that were given, and then to the adjacency list, append those destination nodes. So we would append a pair, or maybe a subarray in this case, where the first value is going to be the destination node, and the second value is going to be the weight, or the cost it takes for us from the source to reach that destination node. So this is just a bunch of setup actually. To actually run Dijkstra's algorithm, it's even less code. Suppose we're given the source node, and in our case it was A. What we would do is first declare our shortest hash map. So for every single node in the graph, we want to map that node to the length of its shortest path starting from A. And we're going to initialize our heap with the cost, the weight of reaching the source node, A in this case, is 0. That's how we're going to initialize our heap. And then we're going to continue the algorithm while our heap is non-empty. What we're going to do is pop from the heap. We know we're going to get the same pair of values that we add to the heap, which the first value is the weight, or the cost. The second value is the node itself. If that node has not already been visited, meaning for that node we haven't calculated the shortest path, then we want to add the shortest path. We're saying this is the cost to reach that node. But if the node was already visited, then we would basically skip this node. We would just go to the next iteration of the loop. Just say, what's the next value we're gonna pop? Because we definitely don't want to overwrite this with a larger weight. That's why we would skip the iteration of the loop. And after we pop a node and get the shortest path and get the length of the shortest path for that node, then we want to go through the neighbors of that node. So for example, for A, we want to go through its neighbors, and each of those neighbors is going to have a node. Remember, that's what we pushed to our adjacency list. The first value was the node. The second value was the cost, the weight to reach that node. So for this neighbor, if for that neighbor we haven't already calculated the shortest path, this is important because we don't want to end up getting stuck in an infinite loop. For example, if, from C, maybe we had an edge going back to A, we don't want to end up, pushing C to the min heap and then pushing the neighbor of C, which is A, and then pushing the neighbor of A, which is C. We don't want to get caught in that kind of infinite loop. That's why we make sure not to push a node that we've already calculated the shortest path for. But if we haven't calculated the shortest path for that node, then we want to push it to the min heap. We want to push that node, but the value that we really care about that we're pushing is the cost to reach that node. What's that cost going to be? If we were pushing E, for example, weight 1 would be the cost to reach C, which was 3. Weight 2 would be the edge cost from C to E, which in this case is 2. We want to add those two values together, and that's the cost that we want to push to the heap. So that's very important, but that's literally it. Then our greedy Dijkstra's algorithm will continue to find the shortest path for every node. And then after our min heap is empty, in this case, that's the conditional I'm using. But another way you could do this actually is by checking that the length of the shortest matches the number of nodes in our graph. That's assuming the graph itself is connected. So we will find a shortest path for every single node. But it might not necessarily be the case. So I think the more general way to write this algorithm is while the min heap is non-empty. And then we will simply return that shortest path hash map. So this was definitely a lot to cover. This is considered kind of an advanced algorithm, but it's not crazy difficult once you can wrap your head around it. It can definitely take time, though. I won't deny that. So it's important to practice. But knowing this algorithm is really helpful. It definitely can come up in coding interviews a lot. It's a really famous textbook algorithm that you definitely want to have in your toolkit.